Assalamu alaikum. Good afternoon, everyone. My name is Lina Al-Atasi. I'm the head of innovation at Oman Arab Bank. Thank you for joining one of the series of the Innovation Hub, the Learning Hub, series. We have a number of Learning Hub sessions running over the next month or so, and we're delighted to be joined by our partners who will be covering various topics around innovation and personal development. We're delighted to be joined today by Mr. Talal Al-Rawajfeh from ProgressSoft, who will be talking about a very interesting topic, artificial intelligence and its applications. I'm sure you'll have many questions to ask during the session. If we could kindly ask you to post these in the chat window or to leave your questions until the end of the session, you'll have the opportunity to ask them live or to post them in the chat window in front of you. So without further ado, Talal, over to you.
Thank you. Hello, everyone, and welcome to this speech on artificial intelligence. To introduce myself again, my name is Talal Al-Rawajfeh, and I'm currently working at ProgressSoft as a research and development engineer. My work at ProgressSoft involves applying artificial intelligence, data science, and image processing to solve different problems within our payment solutions. For example, I worked on signature recognition, handwriting recognition, and document recognition. This introduction is intended to be elementary, and I consider it as an attempt to provide the audience with a broad intuition and perspective on the current state of AI research and applications. Okay, to begin, we will first begin with an apparently obvious question: what is artificial intelligence? As a short answer, AI, as an abbreviation for artificial intelligence, is the simulation and modeling of the human intelligence, particularly by a machine, of course. But what do we exactly mean by a model? A model is a representation or a description of something, like an entity or process. The well-known Newton's laws of motion is an example of a physical model of the universe. The laws describe how objects move and interact together. And not all models are necessarily mathematical. For example, this is a model of an animal cell. Currently, artificial intelligence is a subfield of cognitive science, which is the interdisciplinary study of the mind and its processes. Cognitive science borrows from various fields, such as psychology, neuroscience, computer science, philosophy, linguistics, and anthropology. And to describe something, first you need to understand it, of course. One of the practical goals of artificial intelligence is to implement aspects of human intelligence in computers. So the goal of artificial intelligence is not only understanding intelligence, but also building it. However, here is a question that you could contemplate. Are we intelligent enough to understand intelligence? Now we will talk a bit about modeling the brain. Since it is currently unfeasible to model the entire human brain because of its complexity and our limited understanding of it, we instead start with easier and more simple tasks and try to make abstractions from the observations we make on those tasks and try to see how the essential elements are related and how they interact in a systematic way. Now, what do we exactly mean by a mathematical or logical model? From the abstract and precise nature of both mathematics and logic, we mean that the main elements of the model are abstract mathematical or logical entities that represent real-world entities. And we describe what is modeled by using mathematical or logical relations between these elements and their properties, such as mathematical formulas. As an example, we have Newton's laws again. Newton's laws use abstract single-point masses to represent real-world objects and abstract forces to represent the many different types of forces like gravitation and push and pull and all these types of forces that could act on the objects. Also, the laws make use of an abstract frame of reference to describe motion of objects relative to it. All the interactions between these elements are described by precise mathematical formulas, such as the well-known F equals m times a. Some basic facts about modeling include: One, models don't always exactly represent what is modeled. Sometimes a model is an idealized version of something, such as Newton's laws of motion, or an approximation where the predicted outcomes of the model are close but don't exactly match the real outcome. It is possible for different alternative models to exist, such as general relativity being an alternative to Newton's laws, and three, models could be updated or changed when they don't meet our expectations. This makes modeling a scientific pursuit. That is, we can apply the scientific method to create and update models. We formulate various hypotheses of how we could model something, like an entity or a process, depending on our observations of it, and then we try to test these hypotheses by doing experiments. For example, we make a prediction using the model made from a particular hypothesis, and then we compare its outcomes to the expected real outcomes. The model that survives each test is most likely to be the correct one. Otherwise, we discard or update the model. In this regard, there are benefits from using mathematics and logic for modeling intelligence. Mathematical and logical models in artificial intelligence are easy to test and experiment with, since they could be simulated by a computer. And the computer could perform these calculations in a timely fashion, and the cost of having a computer is relatively and reasonably low. Now we are tempted to ask the question whether AI is possible or not. Fortunately, the history of the field and the current research show that few aspects of human intelligence are possible to emulate by a machine to some extent, which we will talk about later on. However, there is still debate whether many other aspects of human intelligence could be modeled by a computer. These debates involve both philosophical and scientific points of view. One of the most important philosophical debates in this regard is the mind-body problem, which is also known as the mind-brain identity problem. The mind-body problem is concerned with the question whether the mind, which is the faculty of consciousness, thought, and subjective experience, is the same thing as the brain, which is the central organ of the human nervous system. This is because we use the term mind to refer to the subjective aspect of the mind, like what we feel and think and what we are conscious about. However, the brain is something physical, a collection of neurons firing. Could something like that give rise to consciousness, thought, and perception? So, is the mind only a consequence of the brain, or in other words, just interactions between neurons? Can we reduce mind to electrochemical reactions, or is the mind something immaterial? For example, could the mind be an aspect of the soul? These questions are still debated to this day. And although the question of the possibility of AI is still open to this day, for convenience, it was split into two main questions. First, whether strong AI is possible, which is artificial general intelligence, or abbreviated AGI, or full AI. It is a hypothetical machine that has the capacity to understand, learn, and perform any intellectual task that a human can. Second, whether weak AI is possible, or artificial narrow intelligence, abbreviated ANI, or just narrow AI, is the ability to perform specific problem-solving and reasoning tasks that might mimic some aspects of human intelligence, but not all. And it looks like weak AI is less ambitious than strong AI, and therefore less controversial. However, there are also important controversies related to weak AI as well. To point out here, some disagree with this division and think that intelligence must be solved holistically, because that is how the mind works, and we shouldn't divide it into separate problems or tasks. What makes the problem of the possibility of AI even more difficult is the vagueness of the term intelligence itself. Of course, various criteria for intelligence have been proposed, but there is still no single definition that satisfies everyone. On the other hand, there exists wide agreement that for a machine to be intelligent, it must be able to reason, like make logical conclusions from assumptions, use strategy, solve puzzles, make judgments under uncertainty, and it has to represent knowledge, represent knowledge means how to put knowledge into a form that computers could work with. And it has to plan, to be able to learn, to communicate, and integrate these skills towards a goal like a human does. To obtain a better understanding of the problem of the possibility of AI, we need to take a look at the history of the field. An important question here to ask is, when was the first attempt to understand aspects of the mind like thought and reasoning? The most important intellectual work in this regard was the study of formal reasoning, which has its roots in antiquity. In the 4th century BC, the Greek philosopher Aristotle was one of the first to attempt to put the rules that govern correct thinking, which is thinking that yields irrefutable conclusions given true premises or assumptions, which is also called deductive reasoning. His work provided patterns for such arguments structures. For example, Socrates is a man, all men are mortal, therefore Socrates is mortal. He used variables to show the underlying form of an argument, so he was one of the first formal logicians. As an example, here is an illustration of one of the rules that Aristotle's logic included. It is based on the same example in the previous slide. The argument, all men are mortal, Socrates is a man, therefore Socrates is mortal, has a general form, all A are B, X is A, therefore X is B. This is what is meant by formal logic or formal reasoning, which is logic or reasoning that is concerned with the general form of arguments and not a specific argument. In the 3rd century BC, Euclid was the first mathematician who employed formal logic and wrote the most influential books in mathematics, which is The Elements. He started from a few simple and obvious statements called postulates or axioms, which he assumed to be true, and then derived most of the well-known theorems in geometry back then. As an example of an axiom in the Elements was the obvious statements, between any 2 points, a line can always be drawn. Important accomplishments in the 19th century included George Boole developing a binary algebra for formal logic in his book, The Laws of Thought, based on the works of Aristotle and the other formal logicians. And modern propositional logic was developed by Gottlob Frege in his Foundations of Arithmetic. 3, Charles Babbage designed a programmable computer called the Analytical Engine, but was never built. And these accomplishments were crucial to the development of computers, mathematics, and AI. The 20th century was full of many revolutionary achievements within the fields. And the most important included, first, the work of Bertrand Russell and Alfred North Whitehead, called the Principia Mathematica, which revolutionized the foundations of mathematics and formal logic, also called today mathematical logic. Then analytical philosophy was born, which is characterized by an emphasis on language and formal logic. Then Alan Turing proposed the universal Turing machine, which resembles nowadays computers in theory. His work is considered as the basis of the modern theory of computation. And at last, Alonzo Church invented the lambda calculus, which is a formal system in mathematical logic for expressing computation based on few primitive operations that were based on functions. Lambda calculus and Turing machines are equivalent in terms of computational power. To continue the list of accomplishments in the 20th century, David Hilbert, which was also known for his work in the foundations of mathematics and formal logic, challenged mathematicians to answer this fundamental question: can all of mathematical reasoning be formalized? His question was answered by Kurt Gödel in his famous incompleteness theorems. He proved that there are limits to what mathematical logic could accomplish, but within these limits, any form of mathematical reasoning could in fact be mechanized by a machine. The first modern programmable computers were built and they were massive code-breaking machines that were used in the Second World War, to mention Z3, ENIAC, and Colossus. ENIAC and Colossus were developed by the mathematician John von Neumann based on the theoretical foundations of Alan Turing, or the universal Turing machine. Until now, regarding AI, rule-based symbolic manipulation was the key motivation and driving force of modeling some aspects of intelligence. Cybernetics is a field of study that originated from the work of Norbert Wiener in the 1948. It is applicable when a system being analyzed incorporates a closed signaling loop or a circular causal relationship, where the action by the system generates change in the environment and is reflected back to the system through what is called feedback that triggers the system to change. Like how humans affect the environment and the environment affects them back through a feedback loop. The essential objective of cybernetics is to understand and define the functions and processes of a system that are continuously reacting to feedback and to reach a certain state or goal. The field of cybernetics and its methods were very beneficial to AI, especially to what is called today reinforcement learning. Another important field of study that originated in the year 1948 is information theory. Claude Shannon proposed information theory, which studies quantification, storage, and communication of information. It originated from his attempt to find the fundamental limits of the signal processing communication operation, such as data compression. He also founded the digital circuit design theory, which is a model of computation which input values proceed through a sequence of gates, each of which computes a function such as Boolean functions. He estimated the computer playing chess, the complexity of computer playing chess using brute force, which is looking at all possible outcomes of a game to find the best move to play next, which is important for the development of machines that play chess against world champions. Of course, what we can conclude from the previous slides is that the field of mathematics is essential to the study of AI. Fortunately, many mathematical branches were mature by the 20th century and aided the study of AI, such as analysis or calculus, probability theory, and mathematical statistics. Also, statistical methods were discovered and refined, and these statistical methods will become the basis of many algorithms in machine learning. Between 1940 and 1960, scientists from various fields in mathematics, psychology, biology, and engineering began to discuss the possibility of creating an artificial brain. It was known that the brain consisted of neurons, which are nerve cells, and each neuron is connected to other 10 to 100,000 neurons. Signals are propagated from one neuron to another by complicated electrochemical reactions. These signals control the brain activity both in the short term and the long term. One of the first attempts to create a mathematical model of neurons was by Nicholas Rajewsky. Later came Walter Pitts, a student of Nicholas Rajewsky, and his colleague Warren McCulloch, and together they analyzed networks of artificial neurons and showed that they might perform simple logical functions where each neuron was characterized by being either on or off, 1 or 0, from the fact that the activity of the neuron is an all or none process. They were first to describe what later researchers would call a neural network. Later came Marvin Minsky, inspired by Pitts and McCulloch, and built the first neural net machine called the SNARK. Dartmouth Conference in 1956 was a 2-month workshop. It was originated by Marvin Minsky, John McCarthy, Claude Shannon, and Nathan Rochester. McCarthy persuaded attendees to accept artificial intelligence as the name of the field, avoiding associations with cybernetics, and it was widely considered the birth of AI. At the workshop, computers were solving algebra problems, proving theorems in geometry, and learning to speak English, and most people were astonished. Logic theorist LT, a computer program created by Newell and Simon, proved 38 of the first 52 theorems in Principia Mathematica and found new and more elegant proofs for some. Logic theorist is one of the first greatest accomplishments of AI, and it introduced new concepts which were central to AI, which are reasoning as search, like using search trees, using heuristics because search trees grow exponentially, So shortcuts were taken using ad hoc rules, and list processing by the creation of the IPL programming language that processed lists symbolically, because back then programming was difficult and was mainly in assembly language. In 1957, Newell, Shaw, and Simon demonstrated the general problem solver, a universal problem-solving machine, and it applied important concepts such as problem-solving as search and goal-based problem-solving. They also introduced the means-ends analysis technique to control the search, such that given the current state and the goal state, the action is chosen to reduce the difference between the two. In 1958, John McCarthy, also known as the father of AI, invented the Lisp programming language. It was significant for AI because the language supports simple computation and manipulation-based software very well. So it accelerated AI research. There was another great achievement in 1958, which was the perceptron, a model of a neuron created by Frank Rosenblatt. His perceptron made a major improvement over McCulloch and Pitt's model, which could figure out the weights on its own from the data, which is what we call today training, and it could only solve linearly separable problems, but he was optimistic about their power, predicting that perceptrons will be able to learn, make decisions, and translate languages. The perceptron has weights on each input, so it could determine the importance of the input or how much the input contributes to the output, or the degree of correlation between the input and the output. The weights are multiplied by the corresponding inputs, and the results are summed together. Finally, if the result is above a certain threshold, the output of the perceptron would be 1 or on, and otherwise would be 0 or off. Let's see an example of a perceptron. We will create a perceptron that helps us make a decision to buy a car. We want to buy a car for a maximum of $10,000 and a maximum miles per gallon, of 60. We have two cars. The first costs $5,000 and has 40 mpg, and the second costs $10,000 but has 50 mpg. First, we rescale the inputs, the car price and the mpg, by the maximum value to make all inputs in the range between 0 and 1. This is only to make the calculations easier instead of using very large numbers. So 5,000, which is the price of the first car, divided by 10,000, which is the maximum price, equals half. And 10,000 divided by 10,000 is 1. 40 mpg divided by 60 mpg is 0.66, and 50 divided by 60 is 0.83. Here is our car perceptron below, and it has a positive weight on the mpg input, which is 6.25, because the higher the mpg, the better, and a negative weight, minus 6.46, because high prices are not preferable, so they have a negative effect or negative correlation on the output. It takes the inputs, car price and mpg, and multiplies them by the corresponding weights, and then adds the results together. To make the final decision, we look at the sum if it's greater than 0 or not. Here is the actual calculation carried out. On the right, there is a small table just to remember the rescaled car price and mpg. For the first car, the computed value is 0.5, which is the rescaled price, times the weight of the price, which is negative 6.46, and we sum it with the rescaled mpg, which is 0.66, times the weight of the mpg, which is positive 6.25, and the result is about 0.9. And for the second car, the computed value is 1 times minus 6.46 plus 0.83 times 6.25, which is negative 1.27. The first car gives an output greater than 0, so the perceptron fires on. And with the second car, it fires off. So obviously, the final decision is to buy the first car. And that's how, this is the general concept how neural networks today work. Another important contribution to artificial neural networks was the Adeline, developed by Bernard Woodrow and Ted Huff, which used gradient descent on the weighted sum to update the weights. It is different than Rosenblatt's method because gradient descent is used to train the neural network. And it is used till this day to train neural networks. It is a method invented by the mathematician Augustin Louis Cauchy for finding a local minimum of any function numerically. As said before, gradient descent is a method used to find a local minimum of a function, which is just a fancy way to say that we are looking for a minimum near a certain point. Gradient descent could be viewed as moving in the most downward direction. We start from a point and we keep moving downward until we reach the point where we can't go down any further, as you see on the right. As we said about gradient descent, that we want to find the direction that is downward from a certain point, the best way to do this is by using the derivative of the function. A derivative of a function at a certain point is the slope of the tangent line at that point. Basically, this means that it gives the degree of inclination or declination at that certain point, as you see on the right. And we can approximate the slope of the tangent line using the slope of a secant line between the point where the tangent is and another point close to it. As the other point gets closer and closer to the first point, the slope of the secant line gets closer and closer to the slope of the tangent, which is the definition of derivatives today, which is the limit of this process. AI started to gain momentum, and there was an optimism from many researchers that the problem of AI will be solved, and a common belief that it will be solved within 20 to 30 years. Many investors started pouring money into AI. For example, DARPA started investing millions in AI in multiple places, like MIT and Stanford. Sadly, in the 1970s, AI was subject to critique and financial setbacks. AI researchers failed to appreciate the difficulty of the problems they faced, and the field of connectionism, which is modeling the brain by artificial neural networks like we saw, was shut down almost completely for 10 years due to Marvin Minsky's devastating criticism of perceptrons in his book with Seymour Papert, in which they proved that the limitations of using perceptrons for solving some problems as was hoped. And all the programs were, in a sense, only toys and could only handle trivial versions of the problems they were supposed to solve. AI winter basically means that the interest in AI was decreasing and AI funding almost stopped or became very limited, and the hopes turned into despairs. Also, researchers were highly criticized for their unrealistic ambition. There were many limitations and problems that caused the AI winter to happen. And to list a few, first, limited computing power. Computers were still not as we have today. And the intractability of many problems, which required exponential time to find the optimal solution, and the need for large amounts of information about the world. They couldn't solve simple reasoning, language, or vision tasks. And some problems couldn't be converted from informal terms to formal terms, particularly when there is uncertainty. And philosophers criticized the current approaches and even claimed that it is impossible for machines to reach human-level intelligence. One of the important attacks on computer theorem provers and logic-based systems like LT is from the fact that some systems exhibit self-reference, which is paradoxical. For example, there is a paradox that philosophers and logicians call the liar's paradox, where someone says, anything I say is a lie. So if he is telling the truth, then from what he says, he is lying. And if anything he says is a lie, then what he says is true. A contradiction both ways. Kurt Gödel used self-reference to create a mathematical system that could refer to itself, and he used the system to prove incompleteness theorems. Basically, what his theorems imply is that there are some theorems in number theory that are impossible to prove. Therefore, any theorem prover program will go into an infinite loop and will never be able to decide whether the statement is provable or not. After 6 years from the first AI winter, research and applications of AI gained momentum again. However, knowledge became the focus of mainstream AI when expert systems were adopted by corporations. Expert systems emulated the decision-making capability of human experts by reasoning through a body of knowledge represented mainly as if-then rules. Also, programs like Deep Thought defeated chess masters, and many organizations started to fund AI research again. Connectionism revived thanks to the many achievements. First, John Hopfield was able to prove that a form of neural networks called Hopfield nets could learn and process information in a completely new way. Jeffrey Hinton and David Rumelhart popularized a method for training neural networks called backpropagation. Neural networks became commercially successful in programs like OCR, which stands for optical character recognition, and speech recognition. A neural network is just a collection of neurons connected in a certain way called the architecture of the neuron. To understand more about this technique called backpropagation, when training a neural network, the inputs are fed into the neural network and a series of calculations are applied on each layer, as you see on the right, to calculate the output, similar to what we did in the car perceptron, but with many more layers. If the output of the neural network didn't match the expected output, for example, the output was 1 while it was supposed to be 0, then an error is calculated from the difference between the expected output and the actual output from the network. Like if the car perceptron didn't make the right decision on buying a certain car. The function that calculates the error from any given input and its expected output is called the error function. Backpropagation is an algorithm used to calculate the derivative of the error function, and it adjusts or nudges the weights of the neural network using gradient descent, as we explained before, so the error is minimized. On the right hand, we can look at the series of layers as a series of applications of functions, like f of 1 of x, f of 1 of f of 2 of f of 3 of x. So if we apply f1 to x and then we take the result and apply f2 to it and take that result and apply f3 to it, we obtain the value of y. Backpropagation may sound as a fancy term, but and it's always used today in any context that neural networks are mentioned in. However, it is just the chain rule in calculus. Backpropagation is merely a more computer-friendly version of the mathematical chain rule. Just as before, given the composition of functions, and to find the derivative of y with respect to x, we just apply the chain rule as shown below. When using the chain rule, derivation goes backwards in the opposite direction of the output calculation, and that is why it's named backward or backpropagation as opposed to forward propagation. Sadly, the excitement about AI didn't last long again. The business community's fascination with AI rose and fell in a classical pattern of an economic bubble, which made another financial setback for AI research. And expert systems were too complex and difficult to maintain. They were brittle. DARPA again cut the funding deeply and brutally and had decided that AI was not the next wave. Over 300 AI companies had shut down, gone bankrupt, or even had been acquired. Then many researchers deliberately called their work by other names than AI, like knowledge-based systems or cognitive systems or computational intelligence, to procure funding. Also, the universal approximation theorem was proved, which states that neural networks can approximate any continuous functions to a reasonable accuracy. And many achievements were made in this field, in the field of machine learning, such as the invention of the SVM algorithm. And this phase of the AI development could be characterized by the emphasis on machine learning, as opposed to the first phases where the main theme was formal logic and rule-based systems. and this helped the revival of AI again. Machine learning is the study of algorithms that improve automatically through experience. Typically, models are built based on sample data called training data, and the term machine learning was coined by Arthur Samuel in 1959. As we said before, it shifted away from the symbolic approaches and towards methods and models borrowed from statistics and probability theory. The main goal of machine learning is to make models that generalize from the training data. That is, to make models that perform accurately on unseen data, which is just data other than what the model is trained on. As you see on the right, this is what is called a linear regression model, which fits data points by a line that has minimum error. To mention the main approaches in machine learning, there is first supervised learning, where the computer is presented with example inputs and their desired outputs, sometimes called labels, given by a teacher, and which is the programmer himself. And the goal is to learn a general rule that maps inputs to outputs. Then we have unsupervised learning, where no labels are given to the learning algorithm, leaving it on its own to find structure in its input. Unsupervised learning can be a goal in itself, like discovering hidden patterns in data, or a means towards an end, like feature learning. And at last, we have reinforcement learning, where the computer interacts with a dynamic environment in which it must perform a certain goal, such as driving a vehicle or playing a game against an opponent. As it navigates and searches its problem space, the program is provided feedback that is analogous to rewards, which it tries to maximize. As an example of a supervised learning model is a classification model that is trained on labeled pictures of cats and dogs. The model takes a picture as an input and must output the correct class, like dog or cat, and sometimes with a confidence level or a probability. A good example on unsupervised learning is clustering, which is trained on a set of unlabeled points. So it has to figure out on its own how the points are related. Mainly, it tries to divide the points into clusters or groups, such that each group has a common feature, such as their distances apart from each other. As an example of reinforcement learning is a program that plays chess. It learns by playing the game and receiving a negative reward when it loses and a positive reward when it wins. Initially, it plays randomly, and then it starts to learn which moves and strategies are best to play according to the given scenario or state of the game. One of the greatest accomplishments of AI in history was the defeat of the world chess champion Garry Kasparov by Deep Blue. Deep Blue is a chess-playing computer developed by IBM. It was the first computer to defeat a chess champion in both a chess game and a chess match. It was the fastest chess-playing machine at that time, and with its ability to evaluate 200 million positions per second. Afterwards, the progress in deep learning was growing at a fast rate. Deep learning is just the name of various machine learning methods based on artificial neural networks, where the term deep is used to indicate that there are many layers in the neural network, and these layers can learn the essential features from the training set on their own, as opposed to shallow learning, where the features are engineered and handpicked by other methods and then fed into the neural network. Deep learning became more feasible because of the utilization of GPUs for training the neural networks. Also, advances in the computer hardware made the storage of data more efficient, which made large-scale data collection feasible. This is crucial to deep learning because it requires large amounts of data in contrast to many other machine learning methods. Here is an illustration of deep learning in contrast to shallow learning. Above, the features are extracted by many methods other than the network itself, and the network is used only for the decision or prediction. In the bottom, the features are extracted and the decision is made by the neural network itself. The problem with deep learning is that it required much more computational resources than what was available by the CPU. The GPU is more efficient than the CPU in terms of parallel processing of data, since it contains much more cores or processing units. However, each individual core operates on a lower clock speed than the CPU. That is why CPU is much better at sequential operations. For deep learning, the calculation of the output of each one of the inputs could be done separately, since the inputs are independent. Also, many operations could be divided into smaller ones that could be distributed on multiple cores instead of performing the entire operation on a single core. So GPUs were originally intended for graphic applications, but researchers started to use them in 2011 for deep learning. The increase in computer performance made it possible for faster experimentation, and new deep neural network architectures that are more specialized in certain types of tasks emerged. To list one of the few and most important of these architectures is one, the convolutional neural network, which is a deep neural network which is used for computer vision tasks. It uses what is called spatial filters to detect features in images like edges. And two, the recurrent neural network, which is a deep neural network that is used for sequential data that is dependent on time and or has certain ordered structure, like weather data, stock data, speech data, and linguistic data. AlphaGo is a program created by DeepMind that plays the board game Go. Go is much more difficult and complex than chess. And AlphaGo was completely self-taught without learning from human games. Instead, deep learning was successfully applied to create a model that could learn by playing against itself. AlphaGo first started by playing completely random moves, and then it was improving after each game and learning new strategies. And in 2015, AlphaGo defeated Fan Hui, the European Go champion, by 5-0. And in 2016, AlphaGo defeated Lee Sedol, the Korean Go champion, by 4-1. New trends began to appear in deep learning. To name a few, the existence and maturing of many useful open source libraries for machine learning and data manipulation, such as NumPy, SciPy, Pandas, and Theano. And its excellent interoperability with Python, a very simplistic and expressive programming language, which made it easier to experiment with new and ambitious ideas that were extremely hard to implement before that. Also, the creation of TensorFlow in 2015, an open source machine learning library intended for large-scale and distributed machine learning, which is still used today. Before the existence of frameworks, only specialized individuals with PhDs or deep knowledge and understanding of the field could implement such algorithms. Even the experts themselves had a rough time making their ideas work. Deep learning frameworks started utilizing the GPU, which made it possible for anyone to train their models on GPUs. Then research in AI started growing very rapidly, and scientists from many different fields are participating. Many are interested in AI, such as governments, corporations, and even individuals. Now we come to the many applications of AI. The most successful include optical character recognition, OCR, which is the conversion of images of handwritten or printed text into machine-encoded text, such as from scanned documents. Speech recognition, which is the conversion of spoken words to machine-encoded text, like in Google Assistant and Cortana and these types of programs. Face recognition, which is matching human faces and images, and NLP, which stands for natural language processing, which is concerned with the interaction between computers and human language. In particular, how to program computers to process and analyze large amounts of natural language data. NLP is utilized to make chatbots that make conversations with humans translate from one language to another, intelligent autocorrection and autocompletion of text, text classification and summarization, and sentiment analysis. Other applications include making predictions like weather predictions, stock prices, etc., diagnosing diseases, automation of some tasks like in agriculture or manufacturing, in legal analysis, in HR and recruiting, in recommendation like in Amazon or Netflix, in self-driving cars and planes, and in financial services like algorithmic trading, risk assessment, fraud detection, and identity verification, and the list can go on and on. Unfortunately, there are still many limitations and challenges to AI. The current most successful approach to AI is deep learning. And although some deep neural network models have been successful in various domains, they still have limited capabilities. And to mention a few, many companies such as Google had created successful models within the lab environment. However, in the real world, their performance degraded. And making deep neural networks to generalize well is still a challenge. Sometimes deep neural networks could be very sensitive to nuances in data and could fail brutally. Although deep neural networks are powerful, we don't really know or understand how they take decisions and how they extract features from data. Such models are called black boxes, and this raises legal and ethical questions. Although GPUs and software frameworks made things easier, the process of creating models, training them, and testing them still takes a considerable amount of time, especially when the problem is complex. Also, sometimes the data isn't enough or it doesn't have the quality required. There is still no standard method for deploying AI models. And to return to the main discussion, we ask, where are we today in terms of the problem of AI? All the current models used today, such as Google Assistant, are examples of weak AI, but are not good ones. They operate within a limited predefined range of functions, and they are brittle and can fail in unpredictable ways. And we are still far away from solving AGI, or artificial general intelligence. And there is still legal and ethical barriers preventing the application of current models, such as authorizing self-driving cars. To the final question of this talk, is AI overhyped? According to the International Data Corporation survey, 50% of commercial AI projects fail, and this percentage in other surveys and reports go up to 85%. Not every AI company is a research-driven company like OpenAI or DeepMind. Companies want to see a return on investment. However, AI needs time to get better. Sometimes using more primitive approaches in machine learning is significantly better than using deep learning. And the current deep neural network models are just function approximators. They map inputs to outputs, and they don't think or reason like humans do. Sometimes AI is implemented in projects where there is no real need for it, just to attract customers. And here AI is a solution looking for a problem and not the other way around. Some firms even claim that they use AI when they don't actually use it, like a report from venture capital firm MMC Ventures even found that 40% of 2,830 alleged AI startups in Europe don't in fact use any AI in their products. And thank you for listening. And if we want to go to the question Q&A section.
Thank you very much, Talal, for that very insightful presentation.
You're welcome.
We'll open up the opportunity for our participants to ask questions through chat or through live. If you have any questions, please just raise your hand. Whilst our participants gather up their questions, I wanted to ask you, Talal, what recommendations would you give entrepreneurs or innovators who haven't started looking into AI yet and are looking to develop solutions with AI?
Basically, I recommend just learning the basics about artificial intelligence and computer science in general, just so that they could have some sort of concept on how AI works, because many are still not familiar how AI works, and because it can fail, its nature it's probabilistic, so it can make errors, it can work in unpredictable ways. So entrepreneurs have to understand this very well, and have to have a good risk assessment before using any AI in their products.
Great, thank you very much. We have a number of questions from our participants. So the first one is, there are a lot of discussions lately about ethics in technology and AI in specific. How are machines taught or self-taught to produce so-called ethical decisions?
There are many ways to teach a machine, or to tell the machine what is ethical and what is not. But unfortunately, this is all done by hand-coded rules. Like if a self-driving car was driving and it found an old woman and a young woman, and it has to decide whether which one to unfortunately hit. It has to hit one of these, so it must hit the old woman, or what is decided by people, because these problems are very problematic and raise ethical concerns. So they have to encode it into machines. Machines don't understand it, or cannot learn it by its own.
Okay, I hope that answered the question. The second one is from an anonymous.
Okay.
How is AI applied to payments, and what is ProgressSoft or OAB doing today to incorporate AI in their business? I can answer the second half of the question. Perhaps you'd like to take the first half.
Regarding applying AI to payments?
Yes. So how is AI applied to payments, and what is ProgressSoft doing?
Okay, currently we have automatic signature verification, or ASV, which is used to verify signatures on checks. Maybe we are still new to applying AI, but this is one of the products we currently have. Another project we are working on is EKYC, Know Your Customer, which can verify or read information from ID cards, and can make facial recognition to know if this is really your ID card or not, and do other sorts of verifications.
Great, thank you. And perhaps I can just comment on some of the recent launches that OAB has had, specifically on digital onboarding. We were recently the first bank to introduce digital onboarding, especially during the current circumstances and the challenges that customers were facing with their inability to go to the branches, etc. So one of the features we've built into the digital onboarding process is the OCR, which Talal referred to earlier, using AI to be able to verify the user's facial features and to do various KYC checks, etc. And you're more than welcome to go through the entire journey by downloading our app and clicking on creating an account.
Yes, exactly.
We have a number of other questions. So we have a question from Shahed. What are the areas and fields in which artificial intelligence is applied in Jordan?
Well, mainly, I think our company, ProgressSoft, works on image-based problems. So we have signature verification and OCRing and that kind of applications. But other companies, or most of the companies in Jordan, especially who use AI or implement AI, mostly are concerned with NLP, which are chatbots, and what I said on NLP, like translation, Arabic, especially Arabic, because there is a lot of demand on Arabic recognition, language recognition and understanding and translation, especially in speech, like in various applications as Google Assistant and other speech recognition software.
I just wanted to comment on something you've just said when it comes to NLP and Arabic speech recognition. The research has tended to show that accuracy levels when it comes to Arabic speech recognition is very low in comparison to English, for example, because the letters are connected to each other. So it's more difficult for deep learning to happen.
Exactly.
What are some of the advances that are happening perhaps across the Middle East region when it comes to NLP for Arabic speech recognition or text recognition?
Well, I think the most interested companies in, if I can name a company, it's Mawdu', if anyone knows it. And they have a team, AI team, that works on all Arabic language related problems like speech recognition and understanding and automatic completion and all these types of problems.
Okay, great. Thank you very much. Any other questions from our participants? Okay, I think that concludes our session. I'd like to thank you once again, Talal, for joining us, and big thank you to ProgressSoft for partnering with us once again to deliver these Learning Hub sessions. As I mentioned earlier, we continue to announce these workshops via our social media channels and on our website. Please feel free to visit our website to see a full schedule of our upcoming workshops. The registration is open to everyone, and we encourage students, entrepreneurs, and anyone in the public who's interested in innovation or personal development to join these workshops. Thank you all for joining us once again, and we look forward to welcoming you to our next session. Thank you very much, Talal.
You're welcome. Thank you.
Bye-bye. Bye.